continuing our discussion of 2D vectors. Most of our 2D vectors at this point are just going to be force vectors. Many of our vectors will be in the SI units, and so it will be a length of newtons or a length of kilonewtons. You won't often see meganewtons. A meganewton is 10 to the 6 newtons. But newtons and kilonewtons are common in SI. We will also use US customary units. So you'll have a force vector in pounds, maybe a vector in kips. So a kip is a kilopound, which is basically 1,000 pounds. When we get to chapter 3 or part of particle equilibrium, we might have a mass hanging from a cable. And the mass will be given in kilograms. And so the concept of weight is mass times gravity. And so in the SI system, if you have a mass in kilograms, for example, 50 kilograms, and our gravitational constant is 9.81 meters per second squared. And so to convert this mass to a force, to a weight, we take 50 kilograms times 9.81 gives us 490.5 newtons. And so many problems in statics will have a mass in kilograms that you have to convert to newtons for it to be a force. Remember, any number that you write in statics, the number must have units. A number without units makes no sense. We're continuing our discussion of two-dimensional vectors. So we've talked about two-dimensional vector formats. We've talked about how to use your calculator. We've talked about units. We've talked about unit vectors. Let's talk about vector operations. The simplest vector operation is multiplying a vector times a scalar. So you've basically already seen that. So when we basically took, if we wrote an F vector is equal to 100 pounds times a unit vector. So this 100 was a scalar, and this unit vector was the vector. So we've actually already done that, of multiplying a magnitude times a vector. But if you have a force vector that's 20I plus 10J, and you want to multiply that times a scalar, then you just take 5 times that term, and you get 150 in the two components. We basically did that for weight too. So if you take weight as a vector, that's equal to a mass times g. And g is technically a vector that points in the negative or the downward direction. And so that's a scalar times an acceleration to get a weight. You can multiply a vector times 0, and that basically gives you 0. You can multiply a vector times -1, and that reverses the direction of the vector. And if you have a Cartesian vector f, which is equal to 20I plus 10j, and you multiply that times -1, you get -20 minus 10j, and that's basically a force that acts the opposite direction. So -1 reverses the direction of the vector. If you, I don't recommend doing this, but if you have a vector here that's equal to 50 newtons at 30 degrees, then this guy, one way to write him is as -50 at 30 degrees. And so instead of writing him as 50 at minus, if this is 30, this is minus 150, or this is 180 plus, this is positive 210. So you can write him as 50 at 210, 50 at minus 150. or you can write him as minus 50 at 30 degrees. And so if you enter that in your calculator, all three forms, the calculator understands that this is a vector in the third quadrant that is a length of 50 and points in that direction. So vector addition, so those are vector multiplication or multiplication by scalar. So vector addition, because vectors have magnitude and direction, you can't just add their magnitudes. You need a method of addition that accounts for the directions of the vectors as well. So for example, if I have an F1 that's 100 at 30 degrees and an F2 that's 50 at 70, and you say, okay, I'm going to add these two guys together, you can't just go 50 plus 100. To add vectors, there's several different ways to do it. One is graphically. You can use a vector. You can use a vector polygon. You can add these tip to tail. Sometimes it's called the parallelogram law. And so basically, if you're going to add 100 at 30 plus 50 at 70, then you can draw the 100 at 30 and draw the 50 at 70 tip to tail to this guy. And so this guy plus this guy gives you this resultant vector here. And so this resultant here is the sum of this F1 plus this F2. We'll work some examples of this, but basically you build this triangle and then you solve that triangle with law of sines or law of cosines. Kind of painful, but it's a useful check on your problems. It gives you if you draw the vectors to scale and you draw the angles correctly, then it gives you an idea of what that resultant would be. So again, you can add vectors graphically. Another way to add vectors is just use your calculator. And so if you've got this problem and you use the TI-89 or the nSpire, this is 100 at 30 plus 50 at 70. And remember, sometimes I don't write it with the comma here, but for your calculator, it wants the comma. And so you just enter the comma, add these two guys together, and you get 103.7 and 97. And you convert that to polar. So we'll just do that. So we'll basically go on. We'll take control, square bracket, 100, comma, angle symbol, 30, plus control angle, 50, comma, angle symbol, enter, 70, enter. And that gives us 103.7 and 97. And again, my default display mode is rectangular. And if I want to see that in polar form, then I can just go to my functions and I press P, which takes me to my P functions. And I scroll down to triangle polar, enter, enter. And I get 142.0 at 43.1 degrees in polar form. And so that's what this R vector is. This R vector is 142 length, and this angle is about 43.1 degrees. And that makes sense. If you draw these to scale, that looks about right. And so methods for addition, I can do it graphically, which you need to be able to do. You can use your calculator just in polar form. A third way that you can add vectors. And again, if you have a vanilla calculator, standard scientific calculator, then you have to do it this way. Basically, if you take each of these vectors, given as a magnitude and an angle, you have to convert them to x and y components. And so if I have 100 at 30 degrees, its x component is 100 cosine 30. Cosine 30 is 0.866. And so my fx is 86.6. And then I have 100 sine 30. Sine 30 is 0.5 times 100 is 50. And so this 100 at 30 is equal to 86.6 in the x and 50 in the j. This guy here is 50 at 70. So its x component is 50 times the cosine of 70. Or if this angle is 20, then this is equal to 50 sine 20. So the fx is 17.1. The fy is 50 sine 70, or 50 cosine 20, which is 47. And so then these are the x and y components of f2. So once you've converted both of these two x and y components, because the x components all point the same direction, then you can just add this guy plus this guy plus this guy. How many x components you have? Now you can just add those components. And then the y components, because they all act the same direction, you can just add the y components. And so the sum of the x components is 86.6 plus 17.1, which is 103.7. And the sum of the y components is 50 plus 47, which is 97. And so that gives me my FR vector, which is equal to 103.7 and then 97 in the j. If I want to convert this to polar, and again, if I'm using a vanilla calculator, I basically take the square root of 103.7 squared plus 97 squared, and I get 142. Or you can use your TI nSpire or your TI-89 and use the norm function and put in square bracket 103.7, 97, and that gives me 142. And then I can take the inverse tangent of 97 over 103.7, and that gives me the angle. And so this gives me the polar form is 142 at 43.1. But again, like I've shown you, again, you can just use the triangle polar form to convert this xy to polar. So again, you just need to be able to go all three directions, or to convert between all the different vector formats just super easily. So adding vectors, we can add them graphically. We can do it on the calculator and just add them in polar form. Or you can convert every vector to xy components and add the xy components. And you need to be able to do all three. So that's vector addition.